welcome to the This Week in Machine Learning group. Can everyone see my screen?
Yep.
Okay, excellent. So this is what we're going to cover today. We're going to have a review of lesson 2 from the Fast.ai version 3 course. We then have Charles going through, I think it was leather identification. That's how I remember it.
Leather defect identification.
Oh, okay, leather defect identification. And then we'll have Philip, who's going to do a review of an ML paper. Okay, so we ran a little bit out of time the last time round, so I thought it would just make sense for us to skip through some of these steps this time around. Okay, so just a quick recap from last week. We covered lesson 1. Where, sorry, we also did, so init 27, he went through some of the image augmentation and transformations that's available with the Fast.ai library. And lesson 1 was really about getting to grips with the Fast.ai API, things like, the image data bunch, using the from folder, from name with regular expressions and so on. And so on. And so lesson 2 is going to build a little bit on that, where we're going to look at things like putting things into production, but also we're also going to be looking at stochastic gradient descent, and what are some of the things you should be looking out for to confirm whether your model's working as it should. These are just to give you a heads up in terms of who's going to be hosting over the next few weeks. And remember that we meet every Saturday at 9 a.m. US West time, and also obviously if you do have any chat, if you do have any questions and so on, there's a Slack group that you can join. Again, the key thing to remember that is we've got a massive amount of notebooks that you can work through. So please do, if you've got anything to share, please do upload any notebooks and so on. That's just easiest way for someone to be able to verify and confirm some of the stuff that you've found. Okay, so without any further ado, I'm going to hand over to Joseph, who's going to walk us through and provide a review of lesson 2. Again, if you're not talking, can you please go on mute? I'm going to try and figure out how to do this on the, because it just makes it difficult for everyone else who's trying to listen.
Okay, I'm going to share my screen. This is Joseph, by the way. Hello, everyone. So the first thing I'm going to do is just go through, rather than go through notes on what the video said, I'm going to assume that everybody's had a listen to the video, and I'm going to just run through the 2 Jupyter notebooks that are associated with the video, and just maybe we can just discuss what's going on in these notebooks, and then I'll hand it back to John. So the first notebook is, let me share my screen. There. Okay, is my screen being shared? Can people see?
Yes.
Yes.
Yeah, okay. So I'm going to scroll to the top. Okay, so the first thing he does, and this is kind of a really amazing second lesson for anybody who's just started the class, because what you're going to do is you're going to build a multi-class classifier right off the bat, and you're going to even download your own image set of whatever you want to classify, and then you're going to build the classifier. So the first thing you got to do is decide what your classifier is going to classify. What things do you want to do? You want to do cats versus dogs, cougars versus lions, or whatever. I thought I would do a pastry classifier. It's pretty mundane. There's a lot of really much better ideas that are showcased in the forum. But anyway, I'm going to just go ahead with my pastry classifier. I wanted to classify pastries into 3 classes, either donuts, croissants, or bagels. So the first thing I did was I downloaded image data sets of each kind, and they show you how to do it. Jeremy shows you how to do it in this notebook, and it's surprisingly easy after you work through the instructions. But you basically build directories for donuts, bagels, and croissants, and then you just download and dump images into those directories. And then from then on, it's pretty much automatic. The Fast.ai code allows you to, once you've got your images in their separate class folders, it's pretty much automatic from there. You can, it knows how to handle the data from there. So I won't go through all the setup to download the data sets, but I will say that the first pass, I didn't really carefully specify which images I wanted. I did like Google image searches for donuts, and you got a lot of things like you know, plastic donuts and things that really weren't donuts per se. And you can do a lot better by specifying your search terms to eliminate things that you don't want. I didn't do that, but anyway. So there's going through, downloading my images, and then I'll take a look at the data. You know, I'll make a batch of training images, and then I'll just show what they look like. So that's what I'm doing here, so that you can see some of the things that can go wrong. Here's somebody maybe taking a picture of a croissant, and it's not really a croissant. So, but it got in as a croissant. Yeah, here's something that gets classified as a bagel, but it's really a bowl of cereal with some, I don't know, they may be bagels, but they don't have holes in them. And then this is also classified as a bagel. And this, I don't know what this is, but it's classified as a croissant. This is what you get when you're not too careful about your data, about downloading data. There are, like I said, there are things you can do on the keyword searches where you can specify that you want, let's say, art photography or something, and that will get you data that's much closer to what you want. So this just sort of points out that whenever you have a database, you really need to go and look at it, what's in there, and because there could be a lot of problems hiding in there, like this one, this image, for example. So once you start with this pre-trained ResNet 34 model, and it's right out of the box. He's basically taken the ResNet 34 that's trained on ImageNet, and without further ado, he's applying that to this data set here. So it's incredible. Once you've got your images sorted out in these directories, then you run your model, and you can get, I got down to 20% accuracy right off the bat. Now I know that Jeremy's got his example with bears versus whatever. He's got like 4% accuracy, but I still think 20% accuracy, given the noisiness of my data set there, isn't terrible for a three-way classifier. So then he has the thing where you can save your model so that you don't have to run it all over again. Sometimes these models take a long time to run. So you save the model, then you load it again, and it shows you all the layers of, this is something we'll learn about later, all the layers of this ResNet. It shows you, and there's a lot of things going on in this ResNet. So it all shows you all the linear and nonlinear transformations that are going on, all the convolutional operations and so on out to the end. Okay, so the next thing he does is he says, okay, let's unfreeze. What that means is you're going to want to unfreeze the weights and train the model again from scratch. And so that's what this learn unfreeze command does. And I've already done this. And what it does is, let's see, you do this LR find, and it tries to find, it shows you what happens as you change the learning rate. On this axis is the number of, I guess it's the number of iterations. It shows spot right here,
Joseph,
roughly right before. Yeah, hello?
You just froze. I don't know if I'm the only one having the problem or. Yeah.
It's possible. Let's see. Is it unfrozen yet, or is it still?
Yeah, it's great now. Yeah, yeah.
Okay, it must have been a network problem on my end or something. Anyway, so here's the sweet spot, and as we hear 10 to the minus 3, and that's one of the things that Jeremy says is that 3 times 10 to the minus 3 seems to be an ideal. It seems to always more or less work as a first cut, as a first guess. And you can sort of see that
Sorry.
because,
This is
Yeah.
Marcello speaking, so I have a question.
Yes.
Can you repeat what are the two diagrams? Because in the lesson, I remember about the learning rate and the loss. I'm not remembering the other one on the top. What is that? Can you repeat it?
You know, I was thinking about that myself. This is the plot that gets produced by LR. Let's see. That's the first plot, and I'm actually not sure what we are seeing here. Let's see. Yeah, I'm not sure what we're seeing because on the horizontal axis, I don't know what the horizontal axis and the vertical axis represent, but I do know about this plot.
No problem. At least we are the two of us. We don't know. Okay, no problem.
Yeah, but this plot is the second plot is the more interesting one, where you see the
Sure.
loss as a function of learning rate. So here, let's see. I don't know why I did this the second time. It comes out to be similar. Okay, and then he has this special command learn.fit one cycle, and so this number 2 is the number of actually the number of epochs that you want to do. This is the number of times you're going to go through the data. Yeah.
I think that's the plot of the learning rate itself over time, like over the batches, how it's going to increase over the different batches.
Oh, okay. So the
you want
learning
to
rate at
increase
the end goes way up to, but the last value of the learning rate in this plot is 10 to the minus 1, and here it goes up to 0.25.
I think that is to find the learning rate. It needs to increase the learning rate over the batches, right?
Yeah, I think you're right. I think you're exactly right. I think that's what this first plot is.
Yeah.
It's plotting the learning rate. And I think they're deliberately increasing it.
Yeah, so they're going to increase it to a point and until it just shoots off. So
yeah, until the loss starts to explode like that.
And also Jeremy said that in the last, it doesn't show the last few parts of the learning rate because they don't want to, go for the plot.
Yeah, that way this plot wouldn't look, you wouldn't get to see the detail in this part. You're right. So thank you. That's the explanation. Yeah. He's varying the we're plotting the learning rate versus epoch, and they're deliberately changing the learning rate, making it larger and larger and larger until the loss blows up. And then you come back and look at it, and by eye you can pick out what the good learning rate range is. So from this plot, you would think that the good learning rate range is somewhere between 10 to the minus 3 and 10 to the minus 4. I did this. You can actually, I don't think this takes too long. Let's see if we can run this. It's just 2 epochs. So I'm just running this command here. It's going through the data twice. And this thing here, max learning rate slice, this says that it's going to apply the small learning rate to the early layers of the model, and the larger learning rate to the last layer of the model. And the reason for that is you started with this pre-trained ResNet, and it already has presumably pretty good weights in it. You don't want to tweak it too much, so you don't let it vary those weights by too much. That's why I set this. That's why the second learning rate is relatively low. You could actually make it lower. The higher you make it, the more you're retraining from scratch the ResNet. Okay, I'll let that go. I think it's one more time. Okay, next thing, let's see. You save, your second. Once it finishes, you save it, and then you load it again. I'm not going to do that because it's not quite done yet. And then you can come to interpret, like how well are you doing? And this confusion matrix is a really nice way of seeing how your model is doing. I think it actually labels it really nicely. On the vertical axis here is the actual classification of the item, and on the horizontal axis is what you predicted. And so what you would expect ideally is that all of these numbers would be, there would be all diagonal elements and no elements off diagonal, because an off diagonal element means that, for example, here an example that's actually a bagel is classified as a croissant, and that happens twice here. An example that's actually a bagel is classified as a donut, and that happens 5 times. That's how to read this slide. An example that is a croissant gets correctly classified as a croissant 29 times. You can also see here that I don't have a lot of data in my database. I could have downloaded a lot more images, and I would do that on the next pass through. Anyway, is there a question?
Yeah. This is Marcello again. A couple of questions.
Yeah.
One is to my understanding, the classification, the interpretation plot of the confusion matrix is relevant to the validation set, isn't it? Not to the full set, right?
Yeah.
Because it's a small number. While I think the number of pictures you uploaded was much bigger than 20.
Yeah,
or 30.
that's a very good point. The confusion matrix is applied, and it's probably done. This is very slick interface. They've got their own function, and it's probably it is, as you said, it's applying the confusion matrix to the validation set, not to the training set, because we know that the training set's going to be great. What we're interested in is the well, actually, we know all the answers to the training set, so it wouldn't make sense to apply it. Anyway, so yeah, this is the numbers. This is the statistics of the validation set. Run it through our model.
Yeah, actually, yes. And then actually the second question is, I was not able, actually, I'm not really fluent with all the details of the API, so there must be an easy answer reading something more in the documentation. But I tried to apply the confusion matrix, so the classification interpretation, to a bunch of images, which is not in the original data where the learning and the validation that was done. But I was not really able to do that. So
you mean you just took some random images that aren't even, like in this case, bagels or croissants, and just
what I did basically is I did the learning as you did with a bunch of images. Some of them were training set, others are validation set. Then I said, okay, let's pick up a brand new bunch of images, which is where I want to test my learner without any additional training. Yeah. And then I started to go into circles, and I was not able to do that, at least with the interface which was described in the lesson. I don't know if you have any suggestion to do that. Just a matter of waiting for further lessons or
I did this. I did this for individual images. I did this, and I have it down below. So. Is that what you're interested in? Just taking an individual image and applying the classifier?
No, not really. Yeah, the individual images I've seen it's in the lesson, but I was thinking more of a bunch of images, just to make a test on a totally different.
Yeah, that's a good point. I don't know how to do that, but I imagine there is a way. I'll think about it and get back to you on it if I figure it out. But that's a good thing to do, though. Okay, so then let's see. He has this thing next in the notebook that I couldn't get to work. First it was file deleter, and then I found out that that's obsolete. And then image deleter was supposed to work, but that doesn't seem to work either. So it allows you to go through and maybe find images that shouldn't be in the data set and prune them out. That would have been a great exercise for me, because as you see, there were some images that really didn't belong in the data set.
Yeah, I can give you a solution for that.
Yes.
There is a parameter missing.
Yeah.
Yeah, you have to put the root, the root path of your directory tree, and it works. I understand.
It says image deleter is not defined. I don't understand why it doesn't understand what I want here.
Okay,
I think
so
there
you
was
have
a
a
change in
different
the
problem.
update to the library.
Ah, because it's not deleter, it's cleaner.
Image cleaner, is that right?
Yeah, it's changed. The API is changed.
Yeah, they keep changing things around and they don't tell you. That's the thing that's a pain in the neck here.
Yeah, probably. I was able to run this just because I loaded from GitHub only a few days ago.
Okay. I just looked. I was trying to look this morning on Fast.ai what happened to image deleter, and I couldn't find out. So it's called image cleaner.
It is called image cleaner. Yes.
Okay, let's see if that works. Cleaner. Okay. Oh, image missing path. Oh,
And yes, and then you have to put.
Excuse me, if I just wanted to ask, as you was asking about image cleaner, I was trying to run it and there was some issue. I've just posted a question in the general course chat. If someone could help me with that, that would be awesome.
okay.
Which
So apparently I
markup
have
you
to
use?
specify path here. Let's see.
Yeah, path was the one of the parameter which was missing,
Oh,
but
okay. So I could try
after
to
that as well, it's not working. So if
should I do path data?
Joseph, I suggest, you know, if you, why don't we keep moving and then you can come back to the image cleaner.
Yeah, let me just try this one thing. I know this is taking too long, so no, I didn't do that right. So let's just move on. Let's see. The next thing I did was I looked at a few images, of my images at random, and here's a set of, these are all in the donuts directory, so that's why they're all donuts. And then I tried to classify these images one by one. So let's see. I'm going to just try to do that now. On this. For some reason, when Jeremy's spreadsheet, when he did this, it printed an image, and it wouldn't do that for me. So I had to print images by hand. That's what I did up on top. So I'm putting in an image that I want to classify with my model, and I'm going to do that. And then I'm going to classify those three images that I showed up above. And it turns out that my model classifies them all as cross-on, so it's not very good. Or maybe I picked the wrong images at random. Now here comes a really important part of this, which I haven't explored yet, but as you might know or might not know, it's really important for a data scientist to be able to put their model into production and serve it online so that other people could actually play with their model and put in their own images and get them classified and stuff. And that's what this section of code does. And Jeremy puts a link to this really nice web page produced by Simon Willison, who shows how to do this, how to productionize the model. And he made a really nice model. I forget what he's classifying. And he actually goes through all the steps needed to classify it. And if you go over there, I haven't done this, but it'll probably take you an hour or two, or maybe even less. And you can, once you've built a model, you can get it into production. And this is really important. So if you have time after you go through this, the first pass, this is what I would do right after that. I go through and try this. Okay, the next thing that Jeremy does in this spreadsheet is he shows, everything worked really nicely because he already knows what the learning rate should be, that it should be 0.03. And he says that a lot of things can go wrong. If you set your learning rate too high, here's how you can set the learning rate by hand. You're making your model, and you set the learning rate to 0.5, which is a high value. And then you run through one epoch. And then look what happens. The loss starts to really increase, as you could see in that second plot. So this just shows that, and then you have a terrible error rate. It's worse than random. And then he shows what happens. What happens if you set your learning rate too low? So he sets the learning rate to 10 to the minus 5, which is way, as you saw, that's way out of range. It's way towards the left of the range. And then again, you can't get the learning rate to get any better than 61%, which is pretty bad. Then what happens if you have too few epochs? Like if you only run through the data once, again, you don't get a good error rate at the end. And then he shows what happens if you have too many epochs. You can have also a problem where you're maybe overfitting to the data. Here he has 40 epochs. It takes a really long time, so I didn't go through the whole thing. But and that's basically the end of this spreadsheet. So it's good to play with. Once you've understood what's going on in it, I would then try this thing, productionize the model. That's the great next step. Okay, I think I've spent enough time on this one. I'm going to go to the stochastic gradient descent, the second Jupyter notebook here. And what he's doing here is he's just demonstrating stochastic gradient descent, which is a technique for quickly finding the minimum of some function. And so that's exactly what you're trying to do in linear regression. So the first thing he does is he builds a fake data set of points that are along the line. And that's what's going on in these first few frames here. He's building, he's implementing the equation y equals mx plus b, only x is going to be chosen randomly between -1 and 1. And so this is the random data that he's chosen, and he chose the slope. He didn't choose that randomly. He let the slope be 1. Sorry, the intercept. He chose the intercept and set it equal to 1. So this is the implementation of that equation, y equals mx plus b, where x's are random, and m is 3. The slope is 3. As you can see here, it goes from -1 to 1, so that delta x is 2, and delta y goes from the change in y is 6. It's, the slope. Sorry, the change in x is 2. The change in y is 6. So delta y over delta x is 3, which is the slope that is set in there. Okay. So that's what's going on here, and he's just demonstrating this syntax in how you can set up this equation using matrices and matrix operations in Torch. Oh, and then at the end, he's adding some random noise too. And the random noise is between, when you just call the function rand, I think it just gives noise with standard deviation of 1. So that's what's going on here. He's generating some synthetic data, and then the next step is to take some initial guess, and he just pulls a number out of a hat here. The vector, which is the slope and the intercept. He says, okay, I don't know what it is. Let me just make a random, really bad guess. I'll guess that the slope is -1 and the intercept is 1. And so that's what you're seeing here. He then plots that line. This is his initial guess. It has a slope of -1, and it has an intercept of 1, as you can see here, right? So now you use gradient descent, and you do it. You try to minimize the difference between this line and that line, and he writes this little function to do that, and it works really fast to iterate. It basically twiddles the values of your weights, which are the -1 and the 1. It makes small changes in these, and then checks whether that gave you a better answer or a worse answer by calculating the sum of the residuals between the orange line and the sum of the squared residuals between the orange line and the blue line. And if it's better, then it continues and changes it again and changes it again a little bit, and then finally, and very quickly, in fact, you get weights that are consistent with the original equation. So you say, I've got a solution. I fitted that solution. And that's basically the end of that. The last part is kind of trivial. You do an animation to show, and some people might be all interested in that, but I'm not that excited about it. But let's just run through it. So there's the initial guess, and then you step through. I wish you could step through one by one. I'm not sure why you can't. What I want to do is I want to see, oh, maybe I can do that. So each time you make a little change, and the weights get better and better. And after a number of changes, you got really, really close to the original line. You can see that very early in the process, you're already starting to converge. It's really getting better and better and better. And then here it's starting to improve, but much more slowly.
Joseph, I have a question. What's the difference between stochastic gradient descent and gradient descent? Why is stochastic gradient descent better? I mean, gradient descent, I can sort of conceptualize how it works, but what's the stochastic part in stochastic gradient descent?
Okay, the way I understand it, there's 3 flavors of gradient descent. One is just gradient descent, where you step through the entire data set, and then you make your, and then you vary your weights and try to get an answer. That can take a long time to get, especially if your data set is large. So the second flavor is stochastic gradient descent, where you just take one example at a time. You read in one example, you change the weights and then you see if that example, if you got a better prediction for that example. And you step
Okay.
through the examples one at a time. And and the good thing about stochastic gradient descent is that you get immediate adjustments. You can see what's happening right away because you're just adjusting it one example at a time. The bad thing about that is that the examples are noisy. So the adjustments can bounce around a lot from example to example. But so the third flavor of gradient descent is where you do mini batches, where you do a little better than that. You do somewhere in between. You take, instead of taking the entire data set or taking just one point of the data set, you take a small batch, like say 64 examples, and you read in all those examples, and then you adjust your rate based on what you found out with those 64 examples. So this is a sort of a happy medium because you can adjust the batch size to be bigger and bigger and bigger until until it can't fit in your memory anymore. So but if you have a huge data set with say billions of data points and your small computer, you're not going to be able to fit all that data into your memory at once. So you obviously can't do the full gradient descent. So you can adjust the batch size to make it small enough so that it can fit in your memory. So maybe 32 or 64 or 128, and you can tune your batch size. That's one of the tunable parameters that you can play with to see how you can make your solution improve. So I hope that gave you an answer to that.
Yeah, that was very good. But would you say then that gradient descent is in a way better if you would have ultimate and unlimited computing power and memory? Then you should use gradient descent in theory.
You know, I don't know, but I think that's what I can't say for 100%, but I think I'm 90% sure that that's true.
Okay.
I think we're forgetting the stochastic bit. Stochastic implies randomness.
Yes, that's why when you do it one example at a time, that's called stochastic gradient descent because you're getting a lot of noise. When you use the batches, you're doing better than that because if you have 64 examples, then you're basically averaging the noise by square root of 64. So it's 8 times better. The noise is square root of 64 times better, lower that is. If you have 1,028 examples, then the square root of that is 32. Or not 1,024. The square root of that is 32. So you're beating down the noise by a factor of 32. So the larger the batch size, the less noisy it is. And so I would say that I don't know, stochastic gradient descent seems to mean just one example at a time. But in fact, even with any mini batch, you're still getting stochastic noise. So, I would call that stochastic too. I mean, as you said, fiber.
What I know is it picks out a batch at random, and the other variation it goes through sequentially through all of the batches when doing gradient.
I'm
So
sorry.
I think stochastic gradient descent, it picks out a batch at random, and the other variation is it goes sequentially through all of the batches.
Okay, I hadn't heard it done that way. I hadn't heard it defined that way. But the way I had heard it defined, and this is from the deep learning.ai classes that Andrew Ng taught, he said that stochastic gradient descent is one example at a time.
Yeah, but
I think so. Jeremy explains this in the next lecture when he takes SGD in the Excel sheet, I guess.
Okay. Well, we shouldn't get hung up on language on things that don't matter too much anyway. So the big point is that one example at a time is very noisy. 32 examples at a time is less noisy. 64 examples at a time is even less noisy. And all the examples at once is probably something your computer isn't big enough for. That's the takeaway. So that's all I have, and I'll turn it back over to John.
Okay, great. Thank you very much, Joseph. If we can, so Charles, if you don't mind bringing up your notebook about leather defects, that would be great to.
Do I press that green share button?
That's the one, yes. And then you just pick the screen that you want to share. Joseph, you're probably going to have to stop sharing. I don't know whether
I thought I did.
Okay, fine.
Yeah, so I thought I released it.
That's right, yeah.
Okay.
Okay, so we'll start off.
Yes, okay, great. We can see your screen. Thanks.
You can see my screen now?
Yes.
Yes, we can see it, yeah.
Great.
Yeah,
So what I thought I'd do, we're going back to lesson 1 now. And we'd apply lesson 1 to a problem we're trying to figure out at our company, and how to detect leather defects in leather hide for furniture, expensive luggage, automotive. And we've tried and used a lot of commercial software on deep learning software, and nothing has come near to the performance we've had on Jeremy's Fast.ai. So what I'd like to do is just walk you through the train of what I've been doing with the Fast.ai. So the problem is the inspection of leather defects. So let's bring up some examples of leather defects. So if we can get in here.
So Charles, could you provide a little bit more context? Why do you care about leather defects? What's the I mean, as long as it's not sensitive stuff, what's the purpose behind it? What's the business purpose behind this?
Okay, so you've just bought a £200,000 Maserati, and on the steering wheel, on the leather-clad steering wheel, is this pinhole staring at you. By rights, you can turn the whole Maserati back, or get that steering wheel changed. So it can be very, very expensive if you've not detected the defects before they come out of the components of the car. The same applies to high-end luggage, and the same applies to high-end furnishing and shoes, etc. So that's the task, is to find and classify all defects before you've put.
One question. Sorry, I just want to ask: this is a classification problem, or you have solved it as a detection problem or segmentation? So, because your defect, you could have a classification example. You can split the images into parts. That is one way to define it, and you could do boxes also, and then you can do segmentation also. So like what would like you might have tried all of them, but do you have any comments on that?
Yeah, it's a classification problem. If you look at the inset bar here, we want to detect that, but we don't want to detect kind of natural variation in the hide, which is down here. So it's a bit of a tricky problem to do it accurately and well. All this is leather.
So just sorry, Charles, I think you're just sharing a notepad at the moment. So yeah.
I'm showing the so nobody can see what I'm looking at.
No, we can see a notepad.
Oh right. So I need, how do I? Oh, new share. That's what I need to do. I do beg your pardon. Let's go for this one. Can you see that now?
Nope. Now we can see
better now. Yeah.
Now we can see it. Yeah.
You can see leather. So every time I change my screen, I go for a new share. Is that correct?
Oh, I don't know if there's. I think that's true. I don't think you can share your desktop.
Okay.
Yeah.
Every
Yeah, I
time.
think that's...
So, okay. So here is an insect bite. Can everybody see the leather sample I'm showing?
Yes. We can see it.
Yes.
Okay, so here's an insect bite. So it's a classification problem. All this is good leather. We don't want to detect this. This is good leather as well. Maybe on the crease here we want to detect it. My problem was, how do we get to classify all these defects? So we made a...
Sorry, can you show again where the defect is? Because I honestly cannot find.
There's the defect. Can you see it?
Okay. So that small dot there.
That's an insect bite.
Yeah.
There are about 30 different types of defect we need to classify. And so when I started Fast.ai first lesson, I thought this would be right up its street, and it turned out to be the case. So we get those defects into the system. So we built ourselves a thing called a defect, a data set builder. I'll show you the data set builder. Now I'm going to change my screen again. So it's a new share. Oh no. And it is there we go. Okay, can you all see that?
Yes.
Okay. So this is my data set builder. Enter a new block. We'll call it. And we need to build our labels as well. So what we do is just import a set of labels. Okay, can you see the labels now have been inserted?
Yes.
So
Yes.
we've got labels like fine scratches, heel scar, veins, insect bites, pinhole, walk, crease, open area, neck wrinkle, manure, burn, mange, edge, background. The edge and the background is where the scanner runs off the edge of the leather.
So this takes a lot of domain knowledge to be able to classify all of these.
Oh yes, tons of domain knowledge. I can't do it, so we have to throw it back to the leather people who are. Okay.
This is your own data annotation tool, or is it something which is?
I'm a C++ guy, so we knocked this up. This is our own.
Have you come across CVAT, Intel CVAT annotation tool?
No, I haven't. What was that again?
CVAT, CVAT annotation tool. And it is by Intel, and I saw that, and like right now I'm exploring that, and I see it's a pretty good annotation tool.
Right. I'll have a look at that one later on. Okay, so we don't.
Can you write it in the chat, please? Whoever was speaking before about the tool.
Yeah, could you write it in the chat? And
yeah, sure.
Okay, so now what I'm going to do, I'm just going to open some images. So let's take this one. So now we can look for defects. I'm just going to give you a brief one. When we look for defects, we point on the defect, we click, and that will allow us to extract, that's an insect bite, extract a 64 by 64 tile, as it were. And then when we find another one, there's another insect bite here. There's a scar on this one, I think. There's a scar here, can you see the scar? So we'll put a few of these scars on. And so on and forth.
But what makes these so horrible? I mean, it seems to me if I had a piece of leather, a little scar, I mean, there's, leather has a lot of natural markings on it. What's so wrong with a little scar like that or a little insect bite? I don't understand why people would be upset if they saw that.
I've been in the inspection game a long time, and it's purely paranoia.
Really?
You don't want to have, when you're looking at this leather hide, this is an image of what, 1 meter long by 300 millimeters wide. That's $75 in cost. When it goes onto a sports seat in an Aston Martin or something like that, it becomes $5,000. So if somebody complains about that, the manufacturers doesn't really. I mean, it's all about his.
Yeah. But I can just imagine having to throw away, $25, $75 strips could really eat into somebody's profits. Because it looks like, to me, it would look like I would be amazed to see any strip of leather that long that has no defects in it.
Well, I mean, these defects here are perfectly acceptable.
Yeah. Yeah.
But something that's like it's got caught on a barbed wire fence isn't.
Yeah, like a tear, you know, a tear or a hole, that's not acceptable. But just a marking like that, it seems like that should be fine. But I don't know, maybe the people who buy Aston Martins are really picky.
Anyway, shall we move on? We've got, so if I just shrink this down again, so we can see now we're building up a set of classes. We can then save that data set. I won't open another image. I think you've got the idea of what we're trying to do with the data set. So we save that data set. Now the problem is going to be, we're going to get some classes that have got a lot of data in them, and some labels that haven't got any, well, one or two. So at first, Jeremy said, especially in the second lesson, that balanced data wasn't that important. And we found it really, really is. So if we don't balance that data and we just take the raw data, let me just go to another screen and I'll show you what I mean. I'll go here. Go here to data. So when we save the data set, what we generate is the expert selection, which is basically, this is something I've done before. This is the training set that we're going to use to train up on the lesson, in the first lesson, Jeremy's method in the first lesson. So we've got some labels, let's say, of 50, the other labels are only one example of it. So when we apply that expert set to the Jeremy's first lesson method, then we get something like a 28% error rate, which is no good to me. It's no good to anyone. But when we balance the data up simply by finding the largest, let me show you when we go back to, so when we go back to here, if we can balance the data now, so we'll take the highest one, find scratches, and balance everything up to that. Anything that isn't naught, up to that. So insect bites will be just rotated and duplicated. So it's not exactly the same image until we've got 4 examples of it. And then we can also balance it by 10. So that becomes 40, and that becomes 40 by a similar process. So when I do that way, I get a really good data set. And this is where I get kind of a bit scared, because the results we're getting are just kind of amazing. So amazing that I'm suspicious of them. So let's now go to Jeremy's kind of method, and we'll have a look at that. So I'm now going to go to the first lesson stuff. So it is.
So in your training set, how many examples of each class do you have?
Okay, so I've got a maximum of 46 on neck wrinkle here. So I multiplied that out by times 10. So for I think there's 9 classes that are filled. So there's 460 samples for each class.
And you fill out the samples by augmentation?
Yeah, a basic augmentation of mine. I rotate them by 90 every time I copy them. So every copy, every 4, I'm repeating what I'm doing again.
When you are using unbalanced data set, were you using class weights while training?
Sorry, say that again.
So when you are using unbalanced data set, were you using class weights? Because class weight,
something I shall look to. I literally took basically what Jeremy had on his screen and just copied it.
Okay.
I didn't use ClassWork. I'm just trying to find where my Firefox screen. Oh, here it is. So if I new share. How can I get my Firefox screen back? Are you seeing a Firefox screen there?
Nope.
No.
If you share your whole desktop instead of just one program, then you won't have to change sharing every time.
Okay, and where's that?
It's usually the first or the second option in the list of shared screens when you try to share something over Zoom.
Show all windows, is that the one?
I can't see it because I can't share now because you are sharing.
Just bear with me there. So somebody's going to have to give us some help. How do I share this whole desktop?
I don't think you can. I might be wrong. I don't think you have that option in Zoom. So I think you're just gonna.
I have an option on the. It says share desktop, so I think it's possible.
I just want to tell the moderator if my presentation should be today, then.
No, I don't. I think we'll probably move it to next week, and I think we might just have one.
Yeah, John, can we broach while Fiber is looking for his data? Can we broach this one question about how we might want to extend the meeting to an hour and a half in the future, because we have a lot on our agenda. We want to go through the lessons, and we want these extra presentations like we're getting from Fiber today. So what do people think about that, extending the meeting length to an hour and a half?
I think it's a good idea.
Yeah, I think so. Actually, lesson 3 is so dense that it will be tough even 1 hour and a half.
Yeah.
I agree too.
Maybe into the Slack channel.
Have you got that now? It's the Zoom page with the Firefox on. So let's try this one. Look at that. Okay, can you see that?
Nope, still same.
Still the same, so you've not got my Firefox.
Yeah, now we can see it.
Here we go.
Yeah, you got it?
Yep.
Don't ask me how I did it because I don't know. Okay. Right, okay, so here we are. So what we've got is about 8,000 images, I think, in the train folder, and about 2,000 in the
Wow, that's a lot of work.
validation folder. It's not that, maybe I have to go through I have to hand select about 200 defects, and then I just duplicate and augment them. As
I see.
Okay, so let's go from the top. So you probably recognize all of this. It's just one issue further down. Some of this I'm playing around with, so we'll start from the top. So we're using the data sets of the batch size of remember our images are only 64 by 64. They're all grayscale, which is single channel. But there's no color content whatsoever. These are the folders that you probably saw before on the last screens, but they've all been moved now into Paperspace. I think it's in the past, not really important. Some examples of the first few defects. So if we just have a look at these. So this is a neck wrinkle, an insect bite. To tell you the truth, when you look at them, you can't really see much in them. An edge obviously stands out, background obviously stands out. A pinhole is very, very small here. The marker that we use to mark the defect so that we don't go mad, a sample one is there. A heel scar is there. Heel scar is, as the name implies, is a scar that's healed over. Okay, so all the classes we've got. Why is that done that? I don't like messages like that. So these are all the classes. We do have about 20, but only the ones that have been chosen. I've got non-zero entries are here. I've skipped over something here. I didn't really want to skip over that. Loading the CSV file was a real pain in the ass, to tell you the truth. I think I've gone through all the options here, and only this one works. If we just uncomment that and run that, I think it's because it's frozen up because it's running down here. Anyway, let's just look at. I've put 16 epochs in. We start to increase the error rate on the 16th, so that's why I did that. It's getting crazy good.
Jeez.
Now I've run this so many times.
Can you say again how many images do you have in this batch?
There's about 8,000 in the training set and 2,000. There's 10,000 in all. There's 8,000 in the training set and 2,000 in the learning set, in the validation set.
So have you tried using a brand new test, a brand new couple of test images? Maybe that might give you an idea of how well this is doing.
Yeah, we've got an even bigger data set at work. And it duplicates this. It begs the question why we've got such a big data set at work.
So you can build your model with this data set, and then you can apply it to completely new examples from your data set at work, and you still find it does this well?
Yeah, scary. It's scary.
Wow. Okay, well, if that's true, then you've got a great model.
Yeah, I mean, it is really, really good. And what we've been doing is throwing images of totally random, not new images at it, and it seems to pick them out every single time. So here we go. So let's keep going. Just wanted to, if anybody has got any idea on why. I mean, I'm not a great Python guy, so if I was doing this using my kind of domain, which is C++, then I'd be taking the defaults and sticking them in between two things that I wanted to actually change, if you see what I mean. But it just, as soon as I do that. So there's a question for you all. If anybody's got information, let me know. How you see? What I wanted to do was create a different label file to refer to, so I could test it. It'll take the image folder, but not the label CSV file. I've got to keep calling it labels.csv, and then it'll which is the default label, and then it works. Any other way, it doesn't work. It seems to work until you get to the training, and then it bugs out with an error message saying it was expecting a scalar and it's getting a float. So anyway, let's move on. So if we now look at the results, we've got to here, so let's so we've got neck wrinkles and crease. Now, I can't tell the difference between a neck wrinkle and a crease, so I expect some issues there. This one maybe, again, it's a fine scar or a thing, or an insect bite, I don't know. And when we look at the confusion matrix, then, oh yeah, that's pretty good. I mean, this is just the validation set, remember, so there's about 2,000 in there. That's scary good.
Yeah.
That is scary good. Right? And so it gets what I always get mixed up, the crease and the neck wrinkle and the insect bites and the heel scar. I would have said the insect bites. And if I push it forward, I don't know if we've got enough time. If I push it forward, then we start improving on it, and it's I mean, look at this one down here, and so on and so forth. But I think we're running out of time, so I better let somebody get on. I think you've got the gist of what we're trying to do. I don't know. I wanted to really emphasize was this is an amazing tool. This is.
I think you've done a terrific, beautiful example here. I also am suspicious of how good it is, so I would want to check it out. But it looks like it's doing. It looks like it's really doing a great job.
Well, we're going to test it.
Yeah, I agree, Charles. But the thing is, you can't really, or let's compare this to a model where a deep neural net would learn what a banana is and so on. For example, if the Facebook engineers are doing that, then humans could immediately see, wow, this system is so amazing. But in this case, we all had trouble actually classifying what is a word, what is so on. It was actually hard. I remember Marcelo in the beginning actually asking, now where is the disturbance here? Because for me as a human, I mean, you're right that these rich people might actually care about this stuff, but I think the issue is even with the human annotator, quote unquote. But then I would say, if I think about this model, I would actually say the model is kind of better than us humans because it can detect these sort of hidden small disturbances very good, that as shown by your confusion matrix.
Sure, but the thing is, Charles has also used a whole lot of other deep learning models. So this is not the first one he's used. So
we're still not convinced, to tell you the truth, because the next.
Sorry, I have a question here, if I may ask.
Yeah, go for it.
You mentioned that you did some data augmentation to increase the number of images.
Yeah, I mean, it's very simple data augmentation.
Yes. So did the validation set has some of those copies of the original images went to the validation set, or it's
good point.
A different set of images?
So yeah, they will be shared. They will be shared. That's a good point.
Maybe that's why it's so accurate, because it's like the same copy of the image, but it's rotated.
Yeah, it's it could actually be the same image, because we take there's four rotations, so the first rotation is always the same as the original image. So yeah, so that could be the thing. What we're going to do is probe it a little further over the coming month, and with different shades of leather, and see if we can get
Is this something that you're doing just for fun, or you're actually doing it for work?
No, this is a work thing. Yeah, this is a work thing. I just thought, it's
a really fascinating example of what deep learning can do, especially as was pointed out earlier. These defects are so small that the human eye can't always pick them out, but your model can.
Yeah, that's down to the imaging. The imaging is a big. It's like
I'm not sure if you're leaking the training data set into the validation data set, if you're copying some of the images even directly.
And in fact, there is one thing which I think is we have to be careful about, is when we take, let's say, augmentation in the training, there is something we can add the taste time augmentation also. So this I have tried. When I am adding the augmentation in training and testing, train time validation test with the train time augmentation accuracy level would be lower. So it would be like the training would overfit. Like we would get very high accuracy, like 96% accuracy in training, and test would be far behind, like 85 or something. But if I remove the train time augmentation in the same, with keeping the training example same, I would get closer to like 90 or 92% accuracy in the test. So I don't really get why this thing is happening. Maybe just because I am doing augmentation in random, my let's say distribution of the augmentation is such that it doesn't represent the population. So
I don't think I don't understand your result, but I don't think you want to do augmentation to the test data, because the whole point of doing augmentation to the training data is so that you can recognize all kinds of different examples that might be present in the test data. So you don't want to augment the test data.
So, okay. But I was doing that because I just wanted to make sure that whatever augmentation is happening with the trained data, it should represent whatever is happening in the, let's say, real let's say scenario.
Well, I think that applies to your validation set. Whatever you do to the training set, you have to do to the validation set. But I don't think you want to do that to the test set at the end.
Okay.
But I was just going to say for Viber. I'm sorry, I don't know your name.
Charles. I'm sorry. When I was sorry.
Okay, Charles. So the true test of your model is whether it can predict on examples that it couldn't possibly have seen. So data couldn't possibly have leaked from your model into the test. So if you take some absolutely pristine test images that haven't come anywhere near your model and then try out the model on them without incorporating them into the model, that should be a true test. You should still see high accuracy with that, with those predictions.
Yeah, and one of the things I've put into the data set builder is say the residual file. So can you see the screen? I've brought the image back up.
Yes. I see just an image of a high. Yeah.
Yeah. So what would happen if I click on the screen and put, let's say, fine scratch there? Then if I press this button here, options, say residual file, then what it will do, it'll take tiles from the whole image, with the exception of that point there. So that's what we're going to be doing next week, is testing it on all the other image, and we're going to call this image, we're going to class that as good leather, and see if that Jeremy's first lesson model holds up. So if I press this now, I'm going to press it now and probably regret it because it's a big.
So you're producing a whole bunch of data from one image, a whole bunch of images from one image, and since this whole image is good.
Yeah, with the exception of the classes
of the defect. Yeah.
So if I now press the data set builder, or save the data set, it should. It'll split those split those into 64 tiles by an offset, and so.
And each tile is 64 by 64, or?
Yeah, so it's literally going down now, and when it gets to the defect, it stops, jumps over it, and moves on. So that's a way I'm going to use to test it. I haven't used it yet.
But is there a way that you can get absolutely new data that doesn't come from any files in your model? So like if you reserve some of your images.
Yeah, that's what because we're encouraged by this now, so we're busy getting more data in to test it.
Well, this is really interesting. I look forward to see what you have next week.
Yeah, so do I. So yeah, I mean, when I did the first runs, it literally blew my socks off.
So Charles, just one other thing that might help. Perhaps the augmentation can actually be done by the Fast.ai library rather than yourself. That way, you're probably not going to end up with a problem where you're sharing data between your training and training and validation.
Yeah, I've written that down. I made a note of that. Anyway, that rounds it up. Thanks for that.
Charles, have you spoken to the manager of the leather, let's say experts who are doing this? And because with this kind of confusion matrix, I would actually go up to them and say, look at this confusion matrix, and would actually deploy the model if the manager agrees to it. And probably some people are then laid off, but the model is so good that it can be deployed.
Yeah, one day. Yeah, no, we're active in the market, I can tell you.
Okay.
Okay, I'm done.
Okay, thanks, Charles. That was great.
Posted.
Yeah, thanks, Charles. That was great indeed.
Okay, excellent. So apologies, Philip, that we run out of time. I think what's probably going to be sensible is for us to stick to just one presentation per slot going forward, and I think that's perhaps a little bit more realistic. Great. Does anyone want to volunteer for lesson 3?
Is that next week?
Just to clarify, I am preparing for next week then. Did I get that correct?
That's right, yeah. So what we do is, I think, so I haven't read the chats, I'm sorry. So I think there are a couple of things. One is to try and figure out whether we're going to go for 1 hour or 1.5 hours. I think we also need to probably get Sam's permission if there's a cost involved in that, having this longer, and then we probably want to do a poll if people want that. I mean, I think it probably makes sense that if Sam doesn't have a problem, we go for 1.5 hours, and if you only want to stay for 1 hour, just drop off after an hour. It's not a biggie. But I think it helps to have both the lessons and something like this, where you can actually see it working in a real life scenario. I think that's beneficial, or just some other application.
I've actually created a poll in the channel, so please make sure you vote there, and then maybe you could take it up to Sam.
Oh, great. And then I think that even if a majority votes that they only want it to be an hour, I think as long as we're not charged for the extra half hour, some of us could stay for the extra half hour if we want to hear the presentation or another presentation or something like that. Yeah, I don't mind staying for another half hour.
Me too. Also, I was thinking of if it costs money, we could use Skype instead of Zoom.
Mm-hmm. Yeah, I'm hoping it doesn't. Cost money. So we'll see.
Okay, fine. So next week, I'll make sure we find someone to cover lesson 3, and also.
Okay, I'm hosting, and I don't mind covering lesson 3 as well. So.
Okay, fine. And what we'll do is then we'll have Philip. I know that we've also got to do your augmentation piece, Sanyam. So maybe we'll have that as part of lesson 4. And then obviously, if there's anyone else who wants to present something, then you're welcome to. All right, great. So, well, thank you very much, everyone. Thank you, especially Joseph and Charles, for your presentation. That was excellent.
And thanks for hosting, John.
Yeah. All right.
Thanks, everybody. See you.
Okay.